Welcome, everybody. Good morning, good afternoon, good evening for the global reach of our DEHN Protects Lightning Protection Seminar on data center protection. I think that we'll find this is a really exciting and very formative session for the audience today. Thank you very much. I will be asking a few polling questions throughout, but would just ask if you put any kind of notes or comments that you have, you could please put them in the chat area and we'll be able to address that. So data center protection is based on what we like to call the pyramids of pillars of protection. And in this system, it's a very complete approach. We start from lightning risk, and then we move through all the methods it takes to create a protected environment for a data center type application, consisting of all the things you see here: the external protection, grounding, earthing, bonding, and surge protection devices, which would fall under lightning equipotential pillar of protection. And I'd like to use this. There's a lot going on, but this is a great example of that approach for complete protection for infrastructure. And in this case, it even looks like a data center with a nice center protected volume. But it all starts at the outside. You have the air terminal system on the top of the building, down conductors into an earthing system, and equipotential bonding throughout. And what we attempt to do is to create layers of protection. Think of it like an operating room. You don't do the operations at the front entrance at the check-in counter. You have layers of a clean environment, and this consists of grounding, bonding, equipotential bonding, surge protection devices, and bonding of all your metal components. And notice that whenever you go through an area and you enter a more protected area, it's recommended to have that additional layer of surge protection devices. Here we conveniently color them red and yellow for the DEHN product line, but the point is that your power and your data will then be protected coming in and out of these zones, so that you offer the victim, the most vulnerable equipment, the highest order of protection. I like to say it starts with risk analysis. In the IEC methods, it very closely corresponds to the NFPA 780 methods. And really what we do is we evaluate the structure, the contents, the collection volume, the likelihood that you'll be struck in that region of the United States or globally. And we build a risk, and that here you see it colored in red versus the blue chart, where a high risk structure has a risk of loss of life, loss of operation, loss of financial assets. So that risk is compared to an industry tolerable threshold. A customer can select any level of risk they choose and then rerun the calculations. But the industry standards give you a guideline for the tolerable risks. And the intent is to use surge protection and lightning protection methods as a measure to reduce risk. And so here we apply the measures and create an environment that is suitably lower in risk. And then we can define the measures by the application of lightning protection to meet the IEC and the NFPA standards. In a very similar process, NFPA 780 has a calculation method that allows you to use the likelihood of the strikes, the industry, very similar industry standard tolerable thresholds, to apply protection measures to reduce risk below the tolerable threshold. So it's really about understanding your risk and then creating the suitable low risk environment. The prevailing standards that we use as DEHN operational methods include NFPA 780 and the IEC 62305 methods. And here we just have a quick summary of the components and the particular types of standards that fall under this whole category of NFPA protection, with materials, installation methods, and surge protection methods that allow a completely protected system. IEC has a very similar construct of standards and material standards to create a suitable protected environment. Some of the main differences between IEC and NFPA 780 that we discuss that come up a lot, it really comes down to a sort of a philosophy and calculation method. And it starts with a lightning intensity waveform environment. And from the environment of lightning, we can define rigorous calculation methods to deal with the air terminals, the down conductor systems, calculate the separation distance, calculate the amount of earthing that's required, and further calculate how much surge protection the surge protection devices should withstand, right? What type of lightning environment. And from those parameters, you now have a more rigorous calculation method. It attacks risk, it looks at all of the calculations we just discussed, and it proves that the materials are able to withstand the lightning defined environment. This gives us a lot of other calculation tools for things like simulations and other modeling. I like to use this photo as an introduction on lightning because there's really a lot going on, but it gives you a really good picture of who's who in the zoo of lightning. And what I really like to point out is the antenna off to the left is not the main return channel, the main stroke attachment for all that lightning charge. It's a sub-strike, it's a step leader off to the side that didn't form the main channel, but it gives you a really good visual of that electric field that's being propagated in the atmosphere, and charge is moving in step leader jumps through the atmosphere, creating tremendous electric field, finally attaching to Earth, either upward, downwards, lots of flavors of lightning, and then it becomes essentially a DC event where charge moves one way. It doesn't bounce off the ground and go back like an alternating current. It's a DC event with very rapid rise and decay time, but it essentially moves one direction, equalizes the atmosphere for that moment, and gets ready for the next strike. But what you see here is a good indication that visual electric field which provokes the step leader attachment. And so you think of it like a ball of charge that's provoking a huge electric field that's spherical in nature around it. And in that moment that it's attaching, the step leader that is closest wins. All other things like dielectric breakdown of the atmosphere. But Ben Franklin discovered that premise that if you put a lightning rod up higher than the structure, it is likely to strike the rod due to that electric field attachment. And so that rolling sphere is a really good method to apply lightning protection principles. In our NFPA 780 and UL 96 type materials and methods, we use that rolling sphere type method. We also use what's called an air terminal placement method. And that's interesting here down at the left, and it's based much on the known properties of lightning that it's likely to strike the edges. So the coverage in the middle may not actually solve a rolling sphere, but it still presents a very suitable coverage model over a structure. The rolling sphere method is commonly used, as well as this protection angle, that falling angle around something like a tall mast, very commonly seen in the utility sector at switch yards, where there are tall masts around the electric equipment to protect the entire area. And that's much more of like an isolated system where the lightning bolt is attaching to the mast and staying completely away from the structure and the victim. I like to use this illustration as a nice premise of the rolling sphere diameter. And the radius of the sphere increases based on the lower chances of lightning. So the way that the IEC standard describes lightning is we allow for a very small rolling sphere to account for the very upper end small lightning strike diameter. In other words, the smaller the rolling sphere, the more nooks and crannies, the higher the risk. And that's presented by a smaller lightning strike. If you reduce your tolerance of risk and allow for some more risk, you can have a bigger rolling sphere diameter. And that gives you that picture that it won't tuck into as many nooks and crannies. And thereby you won't have as dense of a lightning protection air terminal placement. And this is a nice slide that describes the lightning waveform. In the IEC methods, we use a 10 by 350 definition for lightning. That is, it rises to its peak in 10 microseconds and decays to a 50%, a half value over 350 microseconds. It's a long decay time, but still very short. These are microsecond waveforms. And this we find closely corresponds to the mill standards for what's considered component A, for the duration, the amount of energy, the lightning intensity, the magnitude of the strike. So we like to use that correspondence to help us justify the use of the standards and to offer the mill standard marketplace a much more robust lightning definition. And in the lower right, this is the definition to the classes in IEC. In other words, we say that the highest risk, the class 1, has the highest risk, things like a hospital full of babies and liquid oxygen, or a high value data center operation, where we account for all of the low value intensity strikes and all of the high value intensity strikes. So as your risk tolerance changes, you can tolerate a little bit lower level of protection, which gives you a different calculation method. So just in a quick look at the definitions of lightning, all the sources. Direct strike, where lightning directly strikes a vehicle or your building. Indirect, where it strikes nearby, probably close enough that you still feel the concussion effects. I mean, lightning doesn't have to be very close and still be an indirect coupling. And then all other manner of surges are also addressed, from switching operations on the grid, any sorts of shorting events for fault events, tripping, fuses, parallel installation of power, coupling effects. There's lots of sources of lightning. Want to draw attention to third-party inspection type applications where both the NFPA 780 and the IEC standards are addressed and allow a facility to operate with a master label showing the value of lightning protection to the owners and the operators of the facility. Just like to ask a few questions about why we're attending this seminar. You can put this in the chat or just think about it. That the whole point is I want to engage with the audience to make sure that you're feeling like this is a relevant type of a session for you. And, you know, maybe your reason is that you're bored and you'd like to sit in on seminars, which is an acceptable reason. We like to know that. But really want to understand where the audience is coming from. And I'd also like to point out what are the real concerns? What constitutes the biggest loss in your impression, in your opinion, as data center professionals? Is it the loss of the equipment, or is it the loss of the data? And is there any recovery from this? And further, I'd like to, again, look at the top of the data center and all the way into the middle. What's the most important functional area that needs to be protected? And of course, this is a trick question because it's the entire facility. That's why we take this holistic approach. We look at the entire facility and we can build a protection methodology. And there's some really interesting studies that we've done that look at the distribution of lightning currents in a facility subject to lightning. So take something like a simple structure as this. If you inject lightning into the system from a nearby strike even, where do the lightning currents flow? And when we do this sort of modeling, we find a very striking effect is that we compare two types of systems where it's bonded lightning protection directly into the electrical grid grounding of the structure, or isolated from the structure. And when we look at these system schematics, what we find is the amount of lightning energy that's being injected down into the electrical distribution center. And what we find is that if lightning is coupled into the entire grounding system, you get much higher currents at the distribution center. So it might be a little difficult to see on the black versus white screen, but what we did is we can actually simulate those currents, and what you find is in an isolated system, we're diverting the currents away from the structure, and instead of trying to equally share them throughout the structure. And what we find is that in a bonded system, even though we're attempting equipotential bonding and equipotential grounding, there's still enough impedance through the system that you get significant voltage rises. And in an isolated system, what we find is that the currents are all pushed to the outside of the building and they don't cause voltage rise at the distribution center. And these are modeling systems, and it enables us to visualize what we think is happening at the electrical panels. And this comes back to a couple of questions. How does lightning induce surges? Well, it's all of the above plus more, everything from X-rays to gamma rays, but we have direct coupling, there's electromagnetic induced coupling, and there's ground potential rise, where it strikes nearby and drives the ground up relative to the rest of the building. So what does the air terminal do for you? It gives the lightning a projected point of attachment, a preferred point, and it allows you to build a protected volume of the equipment, chillers, solar panels underneath that set of lightning rods. And if you had electric eyes, you would see that electrical field, the electric field distribution, and the equivalent electric field strength that would otherwise attach to the lightning protection. And this gives us a way to really understand where the lightning should strike and where you can divert it away from a structure. We use similar methods on light poles, where you know it's going to strike probably out there on that light pole anyway. So include it in the system, properly ground and bond it, put up proper air terminals so that we're not obliterating the luminaire systems that sit on the top of these light poles. And so this is some illustration of the types of models that we can apply on a structure and over the entire facility to make sure that you're looking at the entire facility and at a holistic level. And this would include all the transformers, any other solar equipment, these hybrid systems, power generators, diesel backup generators. These all would fall under that zone of protection. And of course, what we're trying to avoid is lightning damage. And in this case, it's not even from the direct strike. This is the flashover from the direct strike. Even if you had a lightning protection system, if the lightning conductors are too close to the electrical systems, and if proper surge protection is not applied, if the bonding distance is too close, if separation is not considered, you can have flashover from the purpose down conductor. There's your lightning protection system trying to do its job, but it's so close to some of this electrical apparatus that it flashes in. And that will cause excessive damage on the inside of the facility that you may not otherwise have suffered. So this is a very common grounding discussion that comes up a lot. How far apart should we keep our buried earth rods? And the rule of thumb is twice the depth of the rod. They should stay apart. So I often see the depth of the rod also used, which is not quite accurate. What you're trying to do is stay away from the influence of the other rod. So grounding systems. In the IEC methodology, we have a couple of ways to look at this, type A and type B. What we find is that this is essentially a single isolated ground rod, which sometimes happens. Not always can they be bonded together around the perimeter of a structure. It just can't happen. In some legacy city urban environments, you're not going to be able to dig up the street and put up a buried type B type ring around the structure. So it's the IEC methods, and you see this as well in the NEC methods. It allows for what essentially becomes a buried electrode. And of course, what we're trying to make sure is that the system is designed for the soil conditions and to meet the lightning protection standards. And if you're familiar with Article 250 here in the USA, it looks very much like a Type A system where there's a single ground rod driven directly at the service entrance next to your meter coming from the utility. And that's it. That's the only thing you might have in your entire house. And this, of course, would be connected to water pipes and other gas metallic feeders coming from the utilities. So the master ground bar is always a very critical element. I'd like to show a couple of images of what it should look like and can look like. This is one you see the large gauge conductor leading down into what's probably the riser coming up from the soil. You have a 2-hole lug, which prevents rotation and helps secure it indefinitely because it's not as subject to vibration conditions, with feeder conductors going to the associated ground bars and equipment throughout the structure. I like to point out that the metallic conductors are bound in at both ends, and that way you don't induce any kind of weird voltages in the metallic conductors that might otherwise flash over. In the IEC methods, it allows us to take a look at the depth and the amount of conductor installed in the soil. So this is a nice chart that we use that looks at the soil resistivity based on the standard, the class of protection standard that you selected from your risk evaluation. And if you're a high risk, then you need more conductor in contact with the soil, and not just the bare minimum that's required by the standard. If you have the very highest risk allowable, you'll see that you're on a much more aggressive amount of conductor that needs to be installed based on the soil conditions. So anything like 1,000 ohm meter soil, which might be a very dry, very, very tough environment, you'll need much more buried conductor in contact with the soil just to meet the lightning protection requirements. So from what type of equipment should a down conductor be separated? Is it from neighboring buildings, trees, conductive parts? Well, the real intent is to require separation from any of these types of structures. What you're trying to do is separate the down conductor from influencing any of the equipment around it. And in our IEC methods, we have a calculation that does depend on the risk and the lightning current, but it also depends on the height and the types of materials that you're subjected to. So with these types of tools, which are very similar to bonding distance calculations found in NFPA 780, we can determine if these apparatus are sufficiently spaced apart. And what you might see on a rooftop is something where you've done a lot of work to create a lightning protection system, but you've got an apparatus that is too close and you haven't maintained separation from that metal fitting. And the whole point is that would then have to be bonded and joined with the electrical protection system, which may not be desirable. You may not want to inject lightning into this. Maybe it's a temperature control box on the roof or a photo sensor or a camera. The point is you may not want to bond and inject lightning into it. So separation and bonding distance are very critical to understand. And in a complicated environment and data centers, you're going to have a lot of opportunity for roof mount chillers and structures that are going to impact the placement of your air terminals. Here's a couple of good examples looking at a mast system that is providing isolation from the lightning protection system between that and the roof mount structures. And what's important to see is that you are still capturing lightning, but you're separating it from the rest of the mechanical systems in the structure. This is a nice illustration of some high performance chillers at a data center where you can see that you're separating the lightning from injecting the chiller. The point is we don't want to knock out the chiller, but we don't want to knock out the electrical system farther in to the structure. We want to keep that lightning energy out. So in this case, we're isolating from the apparatus. This is very common. You see in many environments where you have large chiller structures with cosmetic frames placed around them. And in this case, you have no choice but to have a very much a bonded system. You have so much metal surrounding these structures. If lightning's going to strike, it's likely to strike into the metal, and you would find it's very difficult to isolate away from it. So in some cases, it's a matter of practical and mechanical limitations based on the site itself. So in a breakdown sort of imagery of what's going on at a site, you have an extreme level of detail. You can drive in and look at all of your foundation systems and just make sure that from the ground up, from day one, you built a green field with all the best methodology. And that includes lightning conductor systems built into the vertical pylons that are bonded into the steel and then bonded into the mesh at the base. And we are very confident with some of the clamps that we're using that can be buried directly embedded in the concrete structure. And this creates a very strong, very low potential, very strongly equipotential bonded system to reduce touch-step voltages throughout the site. But then you get to an actual site and reality kicks in, and you find things like broken pigtails, exposed conductors, conductor coming directly out of the concrete where it's subject to stresses from environment, from calcium carbonate, from a lot of just wear and tear. Here you can see the conductor was broken away from the buried bonding system. So we can come up with these elaborate designs, but it's really important to understand what's actually out there. Here you can see off to the right is a really good illustration of bonding plates, grounding plates, where you're using a plate to create the equivalent surface area in an attempt to disperse lightning into the soil in very space constrained and otherwise challenging areas where you can't install other systems. This is a nice illustration of what you actually get at a site, where here we're coupling the down conductor for an isolated lightning protection system in with the existing buried grounding ring at a site. So this is when you really get into the devil of the details. What's the actual conditions at a site? And what can you really do to bond and build an actual grounded system? Here's a few illustrations showing a protection system on a rooftop that has otherwise constraints because of concrete embedments and parking facilities where you can only install into the down conductors into the area that's accessible. In a legacy structure, you may not be able to get to a side that has otherwise been completely filled with concrete or asphalt or other limitations from electrical services. So here we've applied the principles of the lightning protection calculations for the number of down conductors and applied them appropriately to meet the standard, and really is a matter of the challenges that you encounter at a site. Although it's not ideal, you may have down conductors that are near doorways, and then of course you want to properly mark them. But this is a nice illustration that what you would see if you had that electric coverage model built over the structure. And here you can see the walkways and the areas around the doorways are all adequately protected from lightning, protected from direct strike. We like to show the rolling sphere methods applied as accurately as possible on the site conditions to make sure that we've accounted for things like these separate outbound generator buildings. And these are mechanically separate from the structure, but electrically connected. So it's all one part of the larger infrastructure. And there's a lot going on here, but this is a really good typical example of data center complexity, where you have multiple sources of power, backup diesel generators, several levels of generators, utility power with A and B feeders, transfer switches throughout where you have the power source adequately transferred over, multiple levels of surge protection, and then the ideal is that you get right in next to the actual victims inside the structure, the computer systems, the rack systems, that power delivery racks that are spaced throughout the data center, and apply surge protection directly on them to create that electrically stable environment. Because the world is not a nice blue sky day. There's many disturbances, and your system is designed to be extremely robust for power sources, needs to be extremely robust for the surge environment. Here's another sketch with similar applications where you have generators separately feeding the main service entrance, backup transfer switches, backup and battery power supply systems. These are what would be considered electrically very complex. And so what's going to be extremely important to ground and bond those systems adequately. And what we're finding is these systems are having additional resources applied. These data centers may not have started out as a data center. It might have been an office building that's being converted in a metropolitan area. And now you're bringing in additional generators and backup transfer switches, battery systems, rooftop mounted solar systems, solar photovoltaic systems. And all of these multiple sources are not necessarily bonded adequately. So this is an important aspect, is to not just look at the electrical connections, but really go back to the bonding and grounding of these systems and make sure that you have a very rigorous and robust complete system. And that includes the electrical surge protection at the main service entrances and throughout the system on data lines and on the different service entrances and branch panels at each floor. And this is a nice illustration of what some of those legacy buildings look like that have now parking garages, parking structures added with solar collection panels on them. And so these type of applications were never intended for a data center rigorous, a real finely controlled system. And now we're having to upgrade things like the grounding and bonding to make sure that they meet the lightning protection system that's required for a data center. So here's numerous applications where we're finding that the electrical surge protection devices need to be installed. Everywhere from the main service entrance, fire alarm systems, temperature alarm systems, there power over Ethernet security cameras and switches, these systems that are being added have to be protected, and they become part of the overall information gathering system and the building management system, so that you can build a robust management control and know what your limitations are, and know that if lightning is in the area, that you've adequately protected the systems. These are just some very similar images that we see in chiller and motor pump applications, where you're going to have the chiller nearby, and you're going to have data systems next to that equipment to know that it's an operational system. And in this data-hungry world, we want to make sure that we have surge protection adequately applied at all the fire and other sensor control systems. This question comes up very often: is how do I ground my shielding on my instrumentation? Well, the typical rule of thumb is that you apply a shield ground at one end. You ground that shield at, say, the master earthing bar number 1, and you float the shield at the other end, where it might be going off into some other apparatus. And in this case, what we're showing is that you still apply surge protection, and you apply surge protection on that shield. You indirectly ground the shield with a gas discharge tube. And what this acts like, very much like the thermal sensor on a water heater, if there's enough voltage built up, if there's enough pressure on that shield, that spark gap will discharge and equalize the pressure, equalize the voltage on that shield. And otherwise, it stays open, and it does not create a loop or a noisy environment. And just another point out that DEHN is very actively involved in third-party compliance, helping customers get the master label application and installed on their systems for their own peace of mind and insurance requirements. And just a really quick look at what isolated air terminal systems do for other customers. That maybe it's a high value asset like a rocket filled with rocket fuel. So you have a very high risk environment, and in this case, what do the people at NASA do? They apply lightning masts isolated from the system, and these systems create a very clean environment around the launch asset. And this is exactly what you want in any sort of data center environment. So just a quick look at what we covered today. Talked a little bit about the fundamentals of what actually is happening with lightning, and that helps us understand what to do and how to apply the pillars of lightning protection systems. And I'd like to remind the audience today that we have the Florida Professional Board of Engineers credit hours available for this session. Thank you for registering. This is the number that it's under. We'll be happy to provide the suitable certification. And that concludes the recorded session. I'd like to ask my colleague to please halt the recording.